Next talk, I believe, is going to be delivered by two speakers. So this is Marnik and Flaviano José dos Santos from EPFL, and they're going to talk about the AiiDA platform.
So good morning, everyone. First of all, let me thank the organization for giving my colleague Flaviano and myself the opportunity to present our work here today. During our talk, we'll be talking a bit about the various tools and methods that we've been developing in our group at EPFL. And we'll be doing it specifically in the context of a computational database of three-dimensional structures that we've been generating using the AiiDA informatics infrastructure. So our talk will consist of two different parts. The first part will be presented by myself, and the second part by my colleague Flaviano. And in my part of the talk, I'll be talking about this is computational data set of structures that we are generating from three different experimental databases: the MPDS, which is exposing the Pauling file, the ICSD, and the COD. And so in this first part, I'll be talking about, on the one hand, the project overview and the methods we're using. I'll be talking about the computational workflows which we have implemented in AiiDA. I'll also talk about how we process the experimental structures in order to import them into our database, and also talk about the protocols we use to run our calculations. And finally, I'll also, of course, talk a bit about the failures we encounter as we're running these workflows, and a new implementation of a method for improving the robustness of our workflows. So the motivation here is to build a reference database of structures only based on experimental structures, so taken from these three databases that I already mentioned. One important inclusion here is the Pauling file, which is a database that has typically not been investigated so much computationally by other databases. And the second important aspect, of course, here is the assurance of the full reproducibility of our results by tracking all of our calculations in the full provenance using AiiDA. On the other hand, we're also using fully open source codes like Quantum Espresso, so everyone should be able to reproduce the results and the structures that we obtain. And a final important aspect here is a sort of cross-verification with other databases, as we are using Quantum Espresso for our simulation code, whereas other well-known computational databases like Materials Project and Aflolib use VASP instead for their ab initio code of choice. So this is a very interesting way to increase the biodiversity of these databases. For our methods, of course, we're relying on density functional theory as implemented in the Quantum Espresso codes, and we're using the Sirius-enabled version here. Sirius is a library that allows other DFT codes to rely on its algorithms to run more efficiently and easily on new GPU architectures. Using Quantum Espresso, we're relying on the plane-wave Bayes set, and for our pseudopotentials, we're using the standard solid-state pseudopotentials developed in our group, which I'll come back to later. For the functional, we've so far largely been running with PBE. However, we've also recently used a pilot project on a new supercomputer to run PBSol, and in the future, we also hope to include van der Waals and Hubbard corrections in our calculations. So let me talk a bit more about AiiDA. AiiDA is basically a computational infrastructure whose main feature is to track your workflow, so you can design workflows in AiiDA, and then completely automatically track the full provenance of this workflow. So provenance here means basically the history of your calculations. For every step you perform in your workflow, all of the inputs and outputs and the connections between these in and outputs are tracked using AiiDA. So it's implemented in Python, and it has a command line interface and Python API. It's completely open source with an MIT license and hosted on GitHub at the following address. And so besides the full data provenance being tracked by AiiDA, you also have a scalable workflow engine. So you can easily run thousands of workflows consecutively using AiiDA, and its daemon and daemon workers will take care of moving the results to the supercomputer, retrieving the results once the calculation is completed, and storing everything in the database. And so as such, it also has built-in support for HPC, it has support for various schedulers, etc. So it should be easy for you to set up your computer and your code to start running your workflows. And finally, it also has a very flexible plugin system. So this basically means that when you install AiiDA, you just install the core package. But for example, if you want to run Quantum Espresso workflows, you would install the Quantum Espresso plugin package, which then contains plugins for the calculations and data types you need to run your workflows with AiiDA. So in order to construct this database that I mentioned, we start from these three experimental databases, which give us about 900,000 experimental structures. Now, these experimental structures are expressed in a CIF format, and these CIF files tend to have certain issues. So what we first do is use this SIF-clean work chain, completely tracked by AiiDA. And here you can see an example of such a provenance graph that AiiDA generates automatically, where we start by basically fixing some of the syntax issues in these SIF files, then clean up the SIF file by removing unnecessary tags, so we have a uniform format for our SIF files. And then finally, we use a tool called SeekPath, which is also developed in our group, which just takes a structure you have, generates a primitive cell, and also generates a band path, a generalized band path, along which you can calculate the band structure. And so the final structure set is around 860,000 structures. So for most of these SIF files, we do manage to completely parse these and generate the corresponding structure data nodes. And from these, we then remove the non-stoichiometric structures, because we currently do not have workflows that can deal with, for example, partial occupancies or alloys. Finally, we want to do uniqueness analysis. So we use the PyMagen structure matcher utility to compare the various structures we're left with and make sure that we only have one structure for each in our database for which we want to run our workflows. So by doing this, we wind up with this little Venn diagram here, where you can see the amount of structures for each that are unique for each of the databases, as well as the overlap between the databases based on our uniqueness analysis. And you can see, for example, for the MPDS, which is a rather new database we're including here, we have around 20,000 new structures that would be very interesting to investigate for their properties, potentially for all sorts of applications. In total, we have around 300,000 structures, but from these, a lot of them come from the COD in our molecular crystals. So these we are not considering currently for our database. So after removing these, we wind up with around 84,000 structures for which we want to run AiiDA workflows to optimize the geometry. So we do this in several steps. The first step is what we call a reconnaissance SCF workflow. This is basically a static calculation where we just try to give a rudimentary approach to see if a structure is magnetic or not. So we start with a high-spin ferromagnetic configuration and simply do static calculation. If all of the final magnetic moments are below a certain threshold, we can consider the material to be non-magnetic. And if they do have certain magnetic moments, these are passed on to the next step in our workflow. This is then the structure optimization workflow. So here we start optimizing the geometry of our structure. And this also happens in several steps, because in each step of this VC relax process, it's possible that some of the input parameters depend on the volume, and it depends on the structure, actually, the unit cell of the structure. And so we want to make sure this is fully converged. So we check between these VC relax steps to see if the volume has changed significantly. If so, we do another calculation to make sure we really reach the full both structural and electronic ground state. And finally, we also do a final SCF on the final structure we get. We then export and keep the charge density files, and of course, export all of or retrieve all of the interesting properties of the material and store it automatically in the AiiDA database. Now, here you can see for each PW calculation, so each quantum espresso calculation, this is performed in a loop. Because of course, if you're running these kind of calculations high throughput, often you will encounter certain issues. And so what we've developed is a sort of wrapper work chain that recognizes the exit codes that are returned by the calculation. So when AiiDA parses the output file, it can see certain outputs correspond to certain modes of failure. This returns a certain number, an exit code, which can then be captured by this wrapper work chain that can then basically indicate, okay, this is what went wrong. I know how to fix this. For example, the electronic conversions failed. Let me play around with the charge density mixing a bit and see if we can then restart the calculation and successfully get our results. This happens until it doesn't know how to fix the problem twice in a row, or the maximum iterations has succeeded, or ideally, our calculation has completed successfully. And so here you can see a full provenance graph of one of these VC relax workflows. So here's the main workflow that orchestrates all of the sub-processes. Here you have one of these base restart workflows that work chain that wraps our calculation. Our initial calculation failed, so a second calculation has started, which successfully completed. So great, it goes on to the second iteration in the relaxation procedure. And finally, you have the final SCF, which is completed. And then all of this, of course, is automatically stored in the AiiDA database. Now, if we want to run tens of thousands of structures, we're going to need a good set of computational parameters for doing so, because we don't want to complete a full conversion study for all these structures. That would be computationally way too demanding. So here we basically developed what we call a protocol. So this set of computational parameters, which for most of the structures will give us a reasonable precision. For the plane cutoffs, we can rely on the work of two of our former colleagues, Gianluca and Antimo, who have developed a set of pseudopotentials that I already mentioned earlier, called the standard solid-state pseudopotentials, or SSP. These pseudopotentials also come with recommended cutoffs, which they have analyzed in much detail in order to basically get cutoffs that guarantee us a quite good precision when we're running our workflows. For the other computational parameters, we're also relying on a former colleague, Nicola, and his work. He basically took, in Quantum Espresso, a very strict set of convergence parameters, and then for a structure set of diverse structures, slightly relaxed each of these step by step to then figure out, okay, if I compare, for example, the total energy to this very strict set of convergence parameters, what is the error I get compared to that, right? And so here we can see for this sort of K-point grid and smearing, for 95% of structures, we still have a precision within 2 milli-electron volt per atom. Right? So based on this, we have a set of computational parameters, a certain K-point grid spacing, energy cutoff thresholds for the SEF and the ionic convergence. And also for the protocol, we also use this Marzari-Vanderbilt de Vita pane, or more concisely, cold smearing, which will be the topic of Flaviano's part of this talk. And as I'm talking about protocols, allow me to also a brief moment to plug another project which we're working on in collaboration with our good friends at Siesta here in Barcelona. Basically, this project is all about designing common interfaces for certain workflows, right? So the workflow I talked about before was the workflow for Quantum Espresso. But here we want to have a common interface, so with one workflow you can run all of these different quantum engines or quantum codes that are supported currently by the common interface. So let's say you want to calculate the equation state of aluminum and you want to use Siesta as your code. You can simply specify this in this command line interface. And then here again, you can specify the protocol. And so our current protocols for Quantum Espresso are within the code. They're defined within the code. But this will be a very interesting cross-validation again between different codes to see how well our protocols perform when we're comparing results between these different codes. So hopefully we'll be able to come up with a very precise protocol for all these quantum codes that guarantee that your results are also very close to other quantum simulation engines. So what's the current status? Well, so far we've managed to already go to up to 48 atoms in the unit cell, so we've run around 52,000 structures. Of these, around 38,000 have successfully relaxed, right? So this allows us already to do a certain analysis. We, of course, have the corresponding experimental structures in our database as well. So we can start comparing the cell volume with experiment, and we see that there's a slight overestimation of the volume, which is to be expected for the PBE functional being a generalized gradient approximation functional. Now, looking at the success rates, we can see that for the SEF, this is still fairly high, close to 90%. But for the relaxation, we see that often if you're just running with these protocols, all of these experimental structures, there are quite a few failures. And so obviously, we're interested in looking at what kind of failures are occurring here. And so here you can see two pie charts, one for the initial SCF calculation and one for the structure optimization. On the outside, you can see the failure distribution for the various, for the first run, the first calculation, so without any kind of corrections by this wrapper workflow. And we can see that in both cases, the electronic conversion is often the issue here. So it fails to converge to the electronic ground state. Now, in the inner circle, you can see the amount of these failures that our workflow is able to fix. So here you can see that of all the electronic convergence failures, about 1/3 of them we can fix at the work chain level by basically changing the inputs, by changing the charge density mixing. But unfortunately, there are still a lot of unrecoverable errors when it comes to this SCF conversion. So this is something we really want to zoom in on. Now, for the ionic convergence, you can see here that there are a lot of fixes by the work chain, but there are still other error handlers that we have to write in order to figure out how to make also this ionic convergence more robust. So for the electronic optimization, we are working together with the people at CSES who are developing the serious code that I mentioned earlier on a new implementation of a diagonalization algorithm. So instead of using the typical SCF procedure, this loop where you always update the charge density, this procedure tries to basically optimize the electronic wave functions directly using nonlinear conjugate gradient techniques to minimize the free energy of our system. And so looking at some structures here that have difficulty to converge with the SCF, we can see that the corresponding conversions for a direct minimization goes quite smoothly. And I expect at some point 100 structures which fail to converge with the SCF, and we can see that given enough iterations, the NLCG has quite a high success rate. It is able to do the conversions for all the structures using norm-conserving pseudopotentials. But when switching to the SSSP, which also contains ultra-soft and PAWs, we do have a slightly lower success rate, and this is mainly due to failures for the lanthanides, where we have a set of PAWs which sometimes cause convergence issues in our calculations. And so if we would extrapolate, let's say, this success rate, which is rather optimistic, I agree, to our work chains, we would wind up with a 96% success rate for our base work chain, that's the SCF calculation, and for the relaxation, we wind up around 90%. So we started to get closer to an acceptable robustness for running these high throughput calculations. And so finally, of course, I also would like to talk a bit about Materials Cloud, which is the platform we can use to share our results. So if you think of AiiDA as sort of the engine that runs our workflows, you can think of Materials Cloud as the dissemination platform. And there are 5 sections on the Materials Cloud. One is the archive, where you can have large, long-term storage of your data, which is then findable through a DOI. This doesn't have to be data run with AiiDA, but if it is, then you can explore this later on. There's also the Learn section, where you can find all sorts of education material, such as videos about DFT in general, tutorials for QuantEspresso, AiiDA, etc., to develop your skills as a computational scientist. And then in the Work section, there are all sorts of tools for computational scientists. One of them is the SeekPath tool, which I already mentioned earlier in the processing of the experimental structures. And then there's also, for example, the QE input generator, where you can plug in a structure and set certain details of your calculation, and it will generate an input file for QuantEspresso for you. And finally, there are the Explore and Discover sections. The Discover section is basically a way for you to explore curated data sets with an interface that has been designed by people of Materials Cloud. I'll show you an example for a 3DC database in a second. The Explore part of the Materials Cloud allows you to then go to the provenance graph corresponding to this data set and basically explore the different nodes and go back into the history of your calculations to see how exactly everything was computed. So we try to maintain the fair principles when sharing our data on Materials Cloud, and when it comes to the reusable aspect, I would also like to mention quickly AiiDA Lab, which is a Jupyter-based web platform designed in our group to make these workflows accessible via GUI to non-experts. So basically, you can load one of the structures from a database, set certain parameters, and then run a workflow in AiiDA using AiiDA Lab. And so for my final part, let me just quickly give you an example of a current development version of the Discover section for the 3DCD. So you have this typical periodic table where you can select certain elements you want to see inside your structure. And then, of course, if you select a structure, you can see the visualization of the structure, you can see the source, so you can go back to the original entry in, for example, the MPDS. You can see certain structural details, and then if you want to explore the provenance, you can move to the corresponding Explore section. There you can see all of the nodes that are connected, for example, to one of our calculations. You can easily download the input and output files that we use for the calculation, so you can really click on this GUI here and go back to the provenance to figure out all the steps that were taken. So with this, it is my pleasure to pass the word to my colleague Flaviano, who will be continuing with the second part of his presentation.
All right.
There you go.
So testing my microphone. Can you guys hear me? Thank you very much, Marnik. And a very good morning to all of you. So as Marnik was saying, to do all these computations, calculate these properties of so many materials, we had to develop these protocols where we define a set of parameters. And within this protocol, we are using code smearing. This is a technique to improve the convergence when you are doing a sampling of the Brilliant zone with a K-point mesh. So to improve this convergence, we use code smearing. And code smearing has many advantages. However, when you apply it to semiconductors and insulators, both code smearing and metafast Parkinson smearing have a problem of having non-unique Fermi energies. And then today I'll tell you a little bit more how we treated that problem. So to do so, I will first explain what smearing is, to explain for those of you that not know it very well, and what's used for in the context of density functional theory. Then I will explain the different flavors of smearing. There is Fermi-Dirac, cold smearing, and so on. And then explain why some of those methods has multiple Fermi energies. And then finally, I'll introduce the algorithm that we developed to solve this problem, to treat it numerically. And to finalize, I'll show a high throughput study that allowed us to evaluate our proposal and also comparing the new results with previous results. So when you're calculating the electronic structure of materials, we often have to make integrations, and we're integrating quantities that are discontinuous, especially when we are handling metals at 0 temperature. And that's because the occupation function goes to 0 at the Fermi energy in an abrupt way, right? So what smearing does is to introduce a fictitious temperature to your system as to smooth those discontinuities. For example, we can construct a smeared density of state by convoluting the exact density of state with a distribution function, and the choice of the distribution function is going to give you the different flavors of smearing. So for example, you can choose the Fermi-Dirac to have the Fermi-Dirac smearing, and so on. And here's an example of a smeared density of state for bulk aluminum with a finite temperature. And then you see that where you had this discontinuity, now you have something smoother, which make it easier to integrate. So the advantage of smearing, to demonstrate this, I would like to calculate, for example, the forces. So I have here bulk aluminum, and I have displaced one of the atoms in the unit cell by a little bit. So now I'm computing the forces acting on this atom due to the displacement. And then if you were to calculate these forces at 0 smearing, so with no smearing, 0 temperature, you see that your result, your total force, is highly dependent on the K-point mesh that you choose. And this dependency is almost random. It's not systematic. So if you have to do without smearing, you would have to use very fine K-point mesh. So many K-points, so these are very hard calculation to do. So what we do instead is to increase the smearing, and if you do so, you see that all the results with all these K-point meshes converge to a single value. So only then we can say, we can trust, and because here we know that the K-point mesh that we chose doesn't really matter, the exactly K-point mesh. So you have, we can also talk about our converged result, and we can only then compare, for example, my result with somebody else's result, because we know that we are converged with respect to the K-point sampling. Another side effect that you get with smearing that's very favorable to is that it helps to improve the self-consistent convergence. So when you try to find the ground state of your electronic system, you do that self-consistently. And if you were to do with a very low smearing, you see that sometimes I need here 100 iterations, sometimes up to 1,000 iterations to converge. And then when I use smearing, it's always less than 10 iterations. So that's also a good benefit. So it was not meant to do this, but it helps also in this convergence. Okay, now to discuss about the different distribution functions that give different flavor of smearing. So the most natural choice that we could think of is to choose the one that simulates the canonical ensemble. That's the Fermi-Dirac distribution, which I have plotted here for you in orange. So we can also compute the occupation function through this integration here, and then you obtain this orange curve in this figure below. The problem with this method is that this decay here, so this function decays to 0 very slowly. So in your DFT calculation, you would have to consider many electronic states that would be otherwise unoccupied, and this also causes the calculation to be heavier. So what we do instead is to consider all the distribution functions that still satisfy some conditions of a normalization, and also that produce entropy that goes to 0 at 0 temperature. And one of a popular choice to do is to use the Gaussian distribution function, which is plotted here in blue. And you can see that these guys go quicker to 0. Let me demonstrate this a little bit better, because indeed you can rescale the temperature of Fermi-Dirac such as to compare to have very similar curve between Gaussian and Fermi-Dirac. And then you can see this if you follow here the blue line. And then you see that this is very similar to the Fermi-Dirac of this dotted line here. So before I was comparing with the same temperature. You saw they were very different. Now I have rescaled the temperature from Dirac, and now I can make them very similar. But still, if I look how it goes to 0, the occupation goes to 0, I can see that in this logarithm scale, the Gaussian one goes much quicker to 0 than the Fermi-Dirac. So that's why it's more favorable to use Gaussian instead of Fermi-Dirac. Well, using smearing does not only bring advantages, it actually also introduces systematic error in your system. So, and the relevant potential to consider is not the total energy anymore. You have to think about the total free energy of your system. And this total free energy includes now an entropic term. So you have a temperature, you have also an entropy. And each different distribution function that you use defines a different entropy, and therefore your total free energy depends differently of temperature depending on this choice. Let me give you the example of how the total free energy depends on the temperature for Gaussian smearing. So you see here it has a quadratic dependency. So you are putting more and more smearing, increasing smearing temperature, your total energy is changing. However, this change is very systematic. Actually, I can compute it, and therefore I can correct for this error. I can do the calculation with smearing, but still obtain the total energy as if there was no smearing there. So that's very good. The problem that you do this correction a posteriori. And if you were to calculate, for example, forces in your system, you would be using the rogue potential to calculate those derivatives. So to solve this problem, Matfess and Paxton proposed to use an expansion of the Fermi-Dirac distribution in terms of Hermite polynomials. So if using the expansion to the first order, n equal 1 here, you get this distribution function that's shown here. Now, these new distribution functions leave the total free energy independent of the smearing energy up to the third order. So I'm including smearing, so smoothing out the discontinuities, but look, the total energy is not varying anymore, it's constant. Right? So this is very good, very great. However, this comes with a price that the occupation function now is non-monotonic, and even worse, is non-positive definite over here. So you have some negative occupation, and this means that the probability of occupation of some electronic state is negative, so which is unphysical. So this problem here was tackled by Mazzari, Vanderbilt, De Vita, and Payne. They propose yet a different distribution function, which also leaves the total energy independent of a smearing. You can see how this occupation function looks like here. And then, so this is very good. So we have no problem of negative occupations anymore, which makes cold smearing very suitable, for example, to compute forces, and therefore to do molecular dynamics, to do geometry optimization, and so on. But as I'm going to show you next, you still have a occupation function that's non-monotonic, just like you had for Matfess or Paxton. And then what happens is that this non-monotonic behavior, when you are using for insulating semiconductor, can lead to multiple Fermi energies. So the first question that you might make is, why do you want to use smearing for insulators and semiconductor? As I said, no, it's good to use smearing for metals because they have these discontinuities. The thing is that when you're doing high throughput studies, for example, you don't know what's the electrical character of your material. It can be metals, semiconductor, you just don't know. And also during the relaxation, the optimization, you can change this behavior. So you want to be using smearing to be in the safe side, but you want to correct this problem. So how do we actually compute the Fermi energy in these DFT codes? So we actually are computing the total number of electrons as a function of the chemical potential. And in this system of mine here, I'm expecting to have 2 electrons. So this solution here would give you a Fermi energy, something in this plateau, and this one here too. And then you can see that, for example, this solution is actually outside of my band gap. So you could be predicting a material to be metal when it really should be an insulator. And then for code mirror, you have up to 2 solutions. Traditionally, we find this Fermi energy by using the bisection method. So we give an interval that contains the Fermi energy, and we evaluate this equation until we find it to be close to 2, more or less, by subdividing the interval. The problem that this method can give to you this solution, this or this, and we have no way to predict which one of them. It's just going to be random. By chance, you might get the right one. By chance, you might get the wrong one. So to handle this problem, then we focus instead in this function, that the square of the number of electrons as a function of the chemical potential minus the expected number of electrons. And then we do a minimization with Newton's minimization algorithm. So to do so, you need to be able to compute the first and second derivative of this function, which actually you can do analytically, so it's pretty efficient. And here to demonstrate, indeed, this algorithm can find you a solution near to the center of those plateaus here and here. One difference between bisection and this Newton minimization, that Newton minimization needs an initial guess. Instead of you provide an interval, you need to give an initial guess. So then we design this algorithm that first does a prospection using bisection plus the Gaussian smearing. So this also gives you usually a solution within this valley, very close to what we want already. And then you use the minimization to find the minima of your value. You can actually use all the same procedure for Fermi-Dirac, Gaussian code, any smear. So you treat everybody in the same way. So we have implemented this algorithm on Control Expressor right now in the PW code. And it has been released with the version 6.8 of Control Expressor. And actually, I would like to say that we would be very happy to help any developers that with Siesta group, say P2K, if they want to implement also those improvements for code smearing at FASO Pakistan, we are willing to help. So to finalize, we conduct this high throughput study just to analyze the robustness of this algorithm. We used more than 20,000 materials from the 3D database that Marnik was studying. And then we find that we got a different Fermi energy in 20% of those structures. And then what we did, because those structures had been already relaxed with the previous algorithm, and then we computed the forces using the new Fermi energy. And then we saw that for many of those materials, where we saw the discrepancy, actually the forces were out of these convergences. So this force should be near to 0, but actually we're there and finite. So it means that those structures are not really correctly relaxed. So we also analyzed the impact of the incorrect Fermi energy on the band gap. So by correcting it, we saw that we got here, let's say, 5 to 10% of structures within those that we identify with a problem that had a variation in the band gap from 5 up to 25%. Those large variations usually are for band gap that are already quite small. And similarly, we saw that the volume of the unit cell also do change once you correct the Fermi energy. So this is to exemplify which kind of a problem that you would be including in your calculation if you have the wrong Fermi energy. Okay, with that, I would like to summarize our presentation. Marnik started the presentation by introducing to you the 3D-CD project to construct this reference database for 3D materials. Of course, we use AiiDA to keep out the full provenance, and we want to make it available through Materials Cloud. So far, we have focused on geometry optimization and band structure, but we are still developing workflows to calculate more properties to make it available. We focus on determining protocols and improve the robustness of our workflows, and also through the error recovery features from our workflows. He also spoke a little bit about direct minimization that helps to find more easily the ground state. And finally, I showed you a way of improving firm energy determination when we are using methamphetamine and code smearing. So I still would like to thanks to all the collaborations. So this is an effort of a very big group of people. Many of them are working with us in TEOS, our group at PFL. We also would like to thank the Supercomputer Center in Switzerland, the CSCS people. Here is a bit of the AiiDA team that contribute in many various parts of these projects. And I also would like to thank the funding from INTERSECT, Max and Marvel and the Praise projects. So with that, I would like to thank you for your attention and invite Marnik to answer your questions.
Thank you very much. So questions or comments?
I have a curiosity about the first part for Marnik. So you said that when you selected the structures that you try, we discard the off-stoichiometry systems because from the databases, right?
Molecular crystals.
Yeah. So do you have any idea or a plan how to, let's say, introduce not perfectly bulk systems? I don't know, surfaces or off-stoichiometry. It's a mess. I understand.
It's more challenging, for sure.
Perfectly.
For sure.
But so do you have any clue on
So when it comes to two-dimensional systems, we actually have a student coming over from Brazil next year in February. We'll be doing some work on 2D materials, and so we'll be working on basically adapting our protocols to see if we can also start working on 2D materials, which of course be challenging. And then also introduce indeed these workflows for either starting from an already 2D material or starting from a bulk structure, generating a 2D structure, the surface and the slab and everything, and then basically working on this. So there is a plan for 2D structures, and then over time, of course, we hope to be able to deal with all kinds of lower dimensions as well. But this is, of course, going to take a bit more time.
I can imagine.
Okay. I have a question about this occupation smearing. I always have the concern what happens when you have systems in which properties are very much dependent on the Fermi surface. So I'm thinking of, for instance, charge density waves where you have this Fermi surface nesting. Mm-hmm. Is that correctly captured when you have this smearing, where you completely wash out the Fermi surface? So in these metallic systems, what does it happen?
Yeah, I mean, the problem of not using smearing, that it's very, very hard to have a good picture of it if you don't have a very, very fine K-point mesh, right? Now, if you do use smearing, so the question is, do you really capture the physics in the Fermi?
I think maybe when it comes to I mean, I don't have a lot of experience on the topic, but I think when it comes to calculating these Fermi surfaces, you would do a static calculation probably, and then simply use tetrahedron method.
No, but what I mean is there are properties like the energy that depend very much on the shape of the Fermi surface and the details of the Fermi surface. So, for instance, charge density waves is one of them. You distort the system because by distorting the system in that particular way, you open a gap. If you smear out the Fermi surface, do you still capture this energy change with the structure? So
yeah, to be honest, Pablo, I not have the experience to really tell that those properties that depend specifically in the firm surface, how they get affected by smearing. I have the impression that because we use smearing, to help this K-point conversion, but not too high, as not to impact those properties, because smearing really induces an error. And when it's too large, we can't correct for those errors. So we do it we have to find the sweet balance. So that's in the expectations that we won't be affecting those physical properties. But again, how it affects, I do not know. I do not, yes.
So maybe it could be interesting to look at it.
For sure, it's interesting.
For metals. So
yeah, it's a problem to have a look at.
I don't see any other questions. I don't know if the chat has any. No. So there are no further questions. Let's move to the next speaker. Oh, here. Jesper.
Thank you. It was a great talk about the Fermi smearing. You did not say it was unphysical when the occupancy become above 1. Is that simply because it's interpreted as more than 1 electron?
The occupation above
Yeah.
1. Yeah, actually it's this over-occupation that allowed to input in the correction, right? Because we want to add smearing, but still have the total free energy as if there was no smearing. So this over-occupation that actually puts these features there.
The physical
Yeah, you
interpretation,
can
what is
interpret
it?
that as a over-occupation beyond of a given state, yeah. Beyond the max occupation. That's the physical interpretation of it. And then when we had also this negative occupation, as negative probability of occupying something. But so it's kind of, let's say, some physical features that are really to impose some conditions that we want, such as to keep the total free energy independent of smearing.
Thank you.
Okay, so let's thank the speakers again and move to the next speaker.